Tristan.
Wait, so we're not doing the same. We should be like, hello, Christine. Shout out to Tristan.
Right, so we're doing surface area. So you've got used to seeing your three-dimensional objects now, right? Now a cuboid is just a. Over to you. What?
A 3D triangle.
A 3D.
Oh,
This is brilliant. Such a good day. Right, it's a three-dimensional. Well, I guess you could say rectangle, but rectangle is two-dimensional, so you can't really have a three-dimensional, two-dimensional shape. A cuboid is what you would call a rectangular prism, wouldn't you? So it's kind of a box shape. So we use boxes, we use rectangular prisms as boxes. The irregular cuboid, also known as a cube, is just a special cuboid, like a square is a special rectangle where all faces are the same size. Okay? So what you need to be able to do is calculate the surface area of a cuboid at the moment. And to help us do that, that's why we did, first off, the drawing in 3 dimensions with isometric paper to help you visualize. Then we did the plans and elevation to help you visualize a cuboid from its different sides. Because basically the surface area is the area of each face of a cuboid. Right? You all know that anyway, don't you? Is that new to you, or is that fine? Kind of new. Okay. Well, so for instance, if I were to very quickly draw a quick cuboid on, say, 3-dimensionally, right? So you can draw one as well.
Are we recording? No, Sushi will not. Wait, Sushi will not. You may swear. And not swear. Sushi, stop swearing. This is on YouTube.
It just looks, because I'm at an angle, it looks weird to me. Okay, so I have a cuboid. Now, what we've done in the past, obviously, is done our hidden sides, so you know how to draw that. So it's a bit more difficult without the isometric paper, but you get an idea. I'll give you a second to draw your own quickly. We're back in the room. So we've got our 3-dimensional object. Now we've got to work out surface area. Now the whole point of looking at plans and elevation was to get you to start thinking of the different faces. So for instance, we know that with a cuboid all the faces are rectangular. So I can have my shouldn't fill it, I don't want it filled. Well, it's going to be anyway. So I know the front elevation, for instance, will just be a rectangle. Okay? Happy with that?
Yes.
I know the side elevation will be another rectangle. Right? I know the plan is another rectangle. Okay? Right? Something wrong with that one. Can you tell me what it is? Disney?
On the sides of the bottom left, one doesn't match up to the right.
Yeah, so that's supposed to match up there, but I've just not left my space. But again, this type of drawing is not really the objective for today. Is it, Daniel? Okay. So, what is important is we actually... Are you still doing it?
No, no.
What is important is that we get all of the faces sorted. So we've only identified 3. But the fact is that there are how many of these? So there's one here, this end. Oh, there's one more at this end. There, and there's one at the other end, isn't there? So we've actually got 2 of those, one on either end. We've got a B on top and a B underneath. So that would be B, and it's times 2, so I put 2 times A. Got that? And then we've got a C on the side and a C on that side as well. So we've actually got 2 times C. Now, has that got everything considered? Yeah? So, if from my 3-dimensional object, I've got, let's say, 4 and 2 and 7, all right, I should now be able to tell you the dimensions of the rectangles that you'd be able to solve them. So sushi, this rectangle is?
A. And the dimensions of this rectangle.
Diameter is only for circles. So
the dimensions of this rectangle are 2 for the length and 2 for the.
Okay, so it's 2 for. So the area of A. The area of A is what? 2 times 4 makes 8. This one, C, is 2 times 7, which is
14.
Okay. And we've got B on top is
4 times
7 times 4. Okay. Or 4 times 7, which makes 28. So that's the area of each one, but we know we have 2 of those. So our surface area in total is 2 times 8 plus 2 times 14 plus 2 times 28. Make sense? Yeah. Right? Because I've worked out the areas of each face on that cuboid. Got that? Alright, so that's surface area. But what we also need to go down now is think, well, I've done it using my plans and elevations. Right? Got to actually be able to do it using nets. Now, Yagabi and Izzy have started drawing, so what I'm going to do is pause it so that you can all make these notes before I start talking about nets. Okay? Go for it. Right, guys, so next question. So you've worked that out. We've come up with an answer of 100. But what is important when we do these areas is the units. So I haven't given you any units, but let's say that all of these units are centimetres. For instance, 4 centimetres, 2 centimetres. If they are all centimetres, your area must be centimetres squared. Now, if in a test you forget to put your units of centimetres squared or metres squared, you will lose a mark. Okay, unless it's already in the space. If there's nothing there, you will lose a mark. Okay, so simple enough, surface area, but there's one thing that goes along with it, which is the whole point of your egg box challenge thing as well, which is, well, I've done it, set it out here as in its plan elevation, side elevation. However, another way of looking at surface area is to think of your cuboid as a net. Yeah? Do you all know what I mean by a net? Yeah, so explain to me.
A 2-dimensional representation of the...
Not just a 2-dimensional representation.
You can like hold it and kind of
okay,
make
well
it
that's the important thing. Is how would it look if you were to unfold a cuboid? Okay, so basically it's, because obviously these boxes need to go together, so it's about having a flat sheet of paper and cutting it in a certain shape that would then be able to fold up and make the box, so you have less sticking. Because you would say, oh, I just take lots of rectangles, lots of tape, and I'll make a box. But that's not efficient. So we've got to understand that a cuboid can be, right, laid out as a net. Now you need to be able to recognise a net and whether it will work or not. Okay, so there's more than one net for a cube. Does anyone know what a net for a cube would look like? There's quite a few of you would know. Okay, so tell you what, why don't you now, using the rectangle that we've just done, or sorry, the cuboid that we've just done, I would like you to draw the net in however way you want, right? But with the person next to you, can you maybe come up with 2 different nets? So one of you do one, the other one do another, and make sure it's all labelled correctly with the right length. Okay? Or just come up with one and then we'll compare. Okay, so I've started the net. Now what's difficult about a net is you have to kind of visualise what's happening as the shape folds up and which side needs to attach to which side. Right? So for instance, I've started my net, but if you were to look at that, which sides, which faces of the cuboid have I already drawn? You should pay attention to me. Luke.
Everything but the top side.
Okay, so if I asked you to tell me which faces are which, if you look at that, right, so this face is a... So what's it? A letter.
Oh.
A, B or C. So that's a B, you think. Okay? This one is C. This one is... This one is... This one is C. Okay, now, the reason is they all really just fold up, don't they? They just fold up. So if I was going to actually make it, I would need tabs that attach. So this is another thing you have to be able to do. You have to be able to tell me that this side here, this edge, joins with another edge. Which edge would it be? C, or this one? This one? Yeah, so this would match with that one. Right? And if I were to look at this edge, which one does that match with? Yanavi? The A side. So here? Yeah. Okay. So those two match up. Right, what's missing then, again? Thomas?
The top.
The top. So where can I attach the top to? How many options are there? Let me ask you that. Tatiana, how many options have I got for the top?
Two options.
Only two options.
There's 4 options. You can attach it to any side.
So any side. So I can stick it on this one here.
To see this top. For the...
Can I attach the top there?
No.
No, okay.
For the top C.
So here?
Yeah, here. And there.
Here. So any of those sides I can attach the top to. Right? Will it change how I draw it?
Yeah, it will.
So if I say here, what do I have to do? So I have to go out to the same length as B. Or it could be here, but it would only go down, was it 6 squares? So I could have the second B either there or there. Either way, yeah? So that's what you think. You've got a lot more options. Any other way I could change that net, for instance, I could move A now, this one, couldn't I? Sushi?
One thing you could do is make B the center, then put A on each side, and you can attach C to A. So
Yeah.
when they fold up,
So I could
or vice versa.
disconnect C and put it, so join this edge with that edge and have it, yeah. There's lots of ways. Yeah, Thomas?
You could also attach A to the other side of B,
A to,
like to the opposite.
so this one could go over here.
Yeah.
Yeah, you could do that as well. Yeah.
Another thing you could do is attach A, B, and C together.
A, B, and C together.
Which one? Yeah. For example,
So I've got A1, A2, B1, B2, C1, C2. Oh, that's another B2. Just thinking.
yeah. So what we could do is make B the center again. Then attach
Which B?
Which B? The B1.
B1, okay.
Center. Attach A and C2, which or C1. What would actually both of them will do. So let's say C1.
Yeah.
And then You can with A2 you can attach it to C2 and B at the same time.
That's what they said before. I could move this one around 90 degrees
Yeah,
and stick it up
and you
there.
can put it on top. Yeah.
I can't put it there and there
I mean, like, I
at
can
the same time.
I mean, like, in here.
Yeah, well, I think we've covered most options now. I think as long as you are getting the right size. Now, you can use this situation now. So if I get rid of, I'm going to get rid of this one, right? You can use a net also to work out your surface area, can't you? So we can put our dimensions in and we can just work out the areas of each of these faces and add them together like you've done before. Right? So what do you need to be able to do? Well, surface area, easy enough, yeah? With a cuboid. You have to be able to do a net. Now I think you're all you can all visualise. The difficulty comes with nets when you can't visualise how they fold up. Do you know the only way to be able to do that if you can't do it at the moment? Try, actually physically try doing it and imagine, because some people just can't imagine the whole folding up process, they have to do it. Alright, so yeah, if you're in an exam and you're asked to, what shape does this make, does this work? You know, you might get given a net and say, would that make a cube, for instance, or would it be wrong? Some people might have to cut that out and actually do it. But that's not a problem. You know, some people's ability to do that is better at other things than this visual approach. Alright? But if you have to do it, do it. Take a piece of paper, chop out the net and see whether, you can do it very quickly to prove it's not going to work. Very quickly. Alright? Any final questions, should we say, on nets? Question? Okay.
So how does the net alter the density of an object?
Density?
Yeah, because in the Xbox challenge, we will need to consider the
Xbox challenge. Question for your science teacher. Density. What's the density of a net? Well, it's whatever's inside, whatever it's made of. It's not nothing to do with the density. Okay, that's the material. I can take the same net and make it out of cardboard or out of rock or that. The actual, this is just the physical. This will fold up into a box with a space in the middle.
Yeah, so but we need to consider density as well.